Hello, my fine young chemistry students. I want to share with you today a little bit about density. We would be typically working in the lab with some density activities. And so what I'm going to do this year, since I'm not there for the next 2 days, is I'm going to flip-flop some of the stuff that we're doing. So when I do come back, we will be basically doing labs and activities and so forth with these topics. So the first thing I want to show you, though, is with density. Now, you probably look at this picture and you've probably seen this before, and that's called a density stack or a density column. And maybe your science teacher has shown you before. And basically, it's showing you layers of liquids that are sitting on top of one another. And we know that those layers that are sitting on top of another are actually less dense than the layer below it. The more dense layers are at the bottom, the less dense layers are at the top. Now, also, you'll notice some like little objects and stuff throughout there. And there's looks like a screw down at the bottom, a ball kind of floating in that middle red layer. And then you have a ping pong ball. What do you think that ping pong ball is probably going to do? You're right, it's probably going to float right on top. And that's because its mass is very, very small comparatively to its volume. So first off, before we get started, I want to show you just a little quick demo here. And I'm on my front porch this time. And I'm going to show you, I have here a pitcher of water. And you may or may not have seen this before, but I had to look in my fridge and see what the best stuff I had in there was. And my son had this can of Mountain Dew, and it's not diet at all. It's like some kind of funky flavor, Baja Flash. You guys like that kind? And then I have a Diet Wild Mountain Dew, and it's probably from Food City. So anyway, I want to put both of these in the water, and I'm gonna hold them both down for an instant, and then let go. And you'll notice that the Mountain Dew stays, and watch what the Diet Mountain Dew does. The Diet Mountain Dew actually floats, and you'll see that regular Mountain Dew is still staying in there, and it's just hanging out at the bottom. They both are 355 milliliters, 12-ounce cans. We just have to understand, and this is the whole concept of density, is that their masses must be different. And if you guys know anything about diet drinks and aspartame or Splenda or any other like sugar substitutes that are in a soda, those sugar substitutes are very, very lightweight and very low mass. So let's get back to our density discussion then. So first off, you guys probably have known this before through math or science, but density equals mass divided by volume. You guys will definitely want to write down that equation. This will pop up continuously throughout the year and continuously throughout if you take physics or anything else. Density is just super duper common. In this case, the mass is measured with the unit grams. So we know that the base unit is grams, and then we can add prefixes like milli, centa, kilo, all that good stuff. Now, the volume in most cases is milliliters. And like if we're using something like water or a fluid, we can definitely express volume in milliliters. However, if we have something like more tangible or like just the can or a solid itself, say we have a rock, then the volume you would want to convert it to cubic centimeters, because it's kind of silly to, say, hey, this rock is some whatever milliliters. Like, no, that's a solid. So therefore, what you'll find, and you'll want to write this down too, 1 milliliter equals 1 cubic centimeter. So it makes it really easy to have that nice little ratio there. Some tidbits about density, and we'll get into this in just a second. Density is a physical and an intensive property of solution. Now, physical is opposite of chemical, and intensive is opposite of extensive, and we'll talk about those in just 1 second. And this is really, really important. You want to make sure you know the density of pure water is 1.0 grams per milliliter, because a lot of times we compare the density of other objects to pure water. Now let's take a look at that physical and intensive property. Now we know physical property, again, we compare it to a chemical property, But a physical property we can measure, we can observe, but there's no need. Whatever we do to it, we're not changing the chemical identity of the sample. With that, intensive property is a form of a physical property. Intensive is converse to extensive. Now, intensive means no matter the quantity of the substance, the property remains the same. This concept is so very important because what I want you to understand is I can have this pitcher of water, I can have a droplet of water, I can have a pool of water, I can have a lake or a river of water, and if it's pure water, no matter the quantity I have, then the density is 1 gram per milliliter. That's what an intensive property is. It does not matter the quantity. So then you're probably saying, hey, an extensive property must be determined by the quantity. And you're absolutely right. That's the difference between intensive and extensive properties. Now, again, the density equals mass divided by volume, and the density of pure water is 1. So we just have to think about if the density of an object is less, it's going to float in water, like that nice pretty boat and that beautiful water on the screen on the left. Oh, that makes me just want to go on vacation right now. If the density of the object is greater, it will sink in water. And you'll notice that we have this boat or this canoe on the right that's a little too full, and it's got way too much capacity. So those people are going to be floating in their life vests all the way home. But why does ice float in water? So this is kind of interesting because we know ice is just simply frozen H2O, right? So why is it when you pour a cup of water with some ice, your ice floats to the top? Or why is it these icebergs and glaciers and stuff float on top of the ocean? Well, I embedded a video, so let's take a look at this and find out.
Why does ice float on water? To take a sun bath? No, it is because of density. Density is the measure of mass present per unit volume. Lesser the density, lighter is the object. Now, every water molecule has 2 hydrogen atoms bonded to 1 oxygen atom. However, besides being attached to its own oxygen atom, the hydrogen atom is also attracted to oxygen atoms of other water molecules, forming a hydrogen bond. In liquid state, the hydrogen bonds are not strong. They constantly break and reform. Thus, the molecules get arranged in disordered patterns, which leave very less empty spaces. However, when temperature drops below 4 degrees Celsius and ice begins to form, the hydrogen bonds become strong and stable, forming hexagonal patterns which have a large number of empty spaces. These large empty spaces make ice less dense or lighter than water, causing ice to float on water.
All right. So let's go on to the next slide, but I want you to understand what they were talking about there is with the ice, the hydrogen bonds are very important, and that is very early in our semester, but we will learn a lot about hydrogen bonds and how that works. But the hydrogen bonds do create space, and that's what's happening is that we're creating space within the ice, so therefore actually the volume is increasing. Think of it this way. One time, I remember back in college, I had this awesome car. No, it was a Ford Escort, and I could start this car with a screwdriver. Not even kidding. But it drove me places, and I got everywhere I needed to go, and it was paid for. It was all good. So anyway, one day, Mrs. D, living in the great state of northern Indiana, had a can of Diet Coke. And in the winter, I left a can of Diet Coke in the car unopened. What do you think happened to that Diet Coke? You're absolutely right. I got up one morning, got ready to go, face the world, and there was Diet Coke literally covered on the inside of my car. That Diet Coke exploded. Why did it explode? Because when the Diet Coke got so cold and the water actually froze, We know that water expands when it freezes. So therefore, my Diet Coke was all over my car that morning. Again, that made those hydrogen bonds. So let's look at this next one here. And I want you guys today to take some time and really figure out some density calculations. I want us to do this now so that we're ready to do labs and activities and stuff when I come back. And I know you guys can figure this out. So let's take the equation density equals mass divided by volume. And you can algebraically manipulate this equation. Say, for example, we need mass, or say we need volume. So then we just have to manipulate and use density times volume, or mass times density. What you'll see here is this good old little triangle, and you guys may have used something like this before, but notice I put in density equals mass on top divided by volume here. So if you don't love doing algebra, this might be a handy way for you to work through some things. So you can say, okay, I need to solve for mass. So mass equals density times volume, because they're right next to each other in the triangle. If I need to solve for volume, volume equals mass divided by density, because mass is over density in the triangle. You can get the same results by doing it algebraically. You just pick your way that you want to do this, and I don't care which way you do it, as long as you can figure it out and as long as you can manipulate the equation. Now here's a practice problem. So we've got an egg and a mass of 55.5 grams. We know the density is 1.2 grams per liter. We want to calculate the volume of the egg. So we're given the mass, we're given the density. Let's look back at our equations. We're given the mass, we're given the density, we need to calculate our volume. So we're going to take mass divided by density, okay? So look in the little think bubble here. Here's my mass, and basically a lot of students have trouble when the unknown is on the bottom of one of these. So my suggestion to you is pretend this is over 1. And cross multiply and divide. So notice how I set it up in the little speech bubble here. So I set it up as 55.5 grams times 1 equals 1.2 grams times our x. And then I simply solve for x. So I get ultimately 46.25 milliliters. But since I'm calculating the volume of an egg, and it's actually a solid substance, I want to more so express it as cubic centimeters. So I just converted straight up 1-to-1 conversion, 46.25 cubic centimeters. Let's look at another one. So we have a cube of gold, and a cube, hey, has a side length of 1.55 centimeters. So if there's a side length, that means, and it's a cube, all three, length times width times height, is 1.55 centimeters. The sample is found to have a mass. We want to find the density. The only thing we have to do first is we have to determine the volume of the cube, and we have to calculate that before we can actually find the density. So we're going to calculate the volume of the cube, and since we multiply centimeters times centimeters times centimeters, that's why we get the cubic centimeters for volume. And then we take our density equation, mass, 71.9 grams, divided by volume, 3.72 cubic centimeters. So my density of this cube of gold is 19.33 grams per cubic centimeter. That is actually the density of gold. And so if you think about this, what's interesting is it doesn't matter if you have a speck of gold or like a house full of gold, gold is still going to have that same intensive property. The fact that the density is 19.33 grams per cubic centimeter. Let's look at another one. This one's a little bit different, and I know you've done this before, but we have to do a water displacement method because we have an irregularly shaped sample of aluminum. And we put it on a balance and we say, okay, we have a mass of 43.6 grams. So the student decides to use the water displacement method to find the volume. So if you remember the water displacement method, more or less, you have like a graduated cylinder, and in this case, pretend I have my pitcher. And I know when I drop something in my water level will change. So what I want to do is I want to find how much it changes, and that's actually my volume of the object. So the initial, in this problem here, the initial volume reading is 25.5 milliliters. You add the aluminum sample, the water level rises. So we're going to subtract to find the volume there. So let's take a look. We're going to then subtract 41.7, that's our ending volume. We're going to subtract it from 25.5, that's our initial volume. So our volume overall is the change, that's 16.2 milliliters. So then to find the density, we take mass divided by volume. So we have 43.6 grams, that's the mass of the aluminum from the problem above, divided by our newfound volume, 16.2 milliliters. We get 2.69 grams per milliliter. Oops. Let's take a look at this. This is really kind of cool. It's a shrinking styrofoam cup. And of course, like we know styrofoam, and I don't know about you, but I hate that sound when styrofoam scrapes on another thing of styrofoam. It makes my skin crawl. It's kind of like dragging your nails across a chalkboard or something. But this is really cool, and this is Steve Spangler. So let's take a watch on this one.
Says fun more than a pressure cooker and a styrofoam cup. So here's what we did. We went to a viewer's home and got this video. Take a look. Okay. All right, so I think we found everything we need. We found a viewer that had a pressure cooker, a stove, and an unlocked back door. These are all the ingredients, right? So here's what's going to happen. We put a little bit of water at the bottom of the pressure cooker, so we do that. And now I'm going to take this little Corningware and put it here. And now our styrofoam cup goes here. Put the lid on top. And now the little thing here, and now we just set it over here, and we wait for about 10 minutes or so. What?
If you don't know who Steve Spangler is,
right,
he's kind of like the new Bill Nye.
We're going to take it off over here. Very carefully, we have to release the pressure. So it's hot water, and now we release the pressure. Now for the big reveal.
What are you doing?
What a
nice lady.
Nice lady.
And an unlocked back door.
It's from my sister-in-law, and she was okay with that. All right, so I just said I need to kind of borrow the stove. You know, ready for the big reveal?
I am. I want to see what
So
happens.
this is after about 10 minutes. Ready? Watch it. Here it is. Take a look. Go ahead. Pull it out.
Get out.
I'm serious. Take it out. Take a look.
No way.
Yeah.
Is
There
that
it
what
is.
happens?
Your miniature cup.
Look
Isn't that
at that.
great?
Look
So
at
this is
this.
how we started, and there's your miniature
You
cup.
are kidding me.
Literally, all of that vapor pressure that's inside that water vapor presses and compresses all the little spaces that are in styrofoam. Styrofoam is called polystyrene. It has polystyrene is a polymer that has gas blown into it, and so that's what it looks like.
There's that much air in
There
water.
is. Do you remember on the show before we've taken this and put it in fingernail polish remover acetone?
Oh, right, yeah.
We wanted
It
to dissolve.
dissolves.
We didn't want it to dissolve. I think it's really cool how it maintains the shape. And the secret, believe it or not, was this. When I just put it in the pressure cooker, because I've done this now many times today, I melted it. So I made this one. But that's a Christmas tree.
It stays just perfect with when it's in the
and
cup.
this one melted as well. But we started here and started a little larger.
Oh,
pressure
yes,
cooker.
oh, yes,
So you see
right.
what happens.
Yes.
If it's set upright just like this, we get this great little science experiment where we compress the gases. And you can tell it's melted a little bit. If you leave it in too long, it will completely melt. So there's kind of
Okay, what I want you to focus on is he's talking about you compress the gases. So when you compress the gases, are you taking out mass or are you taking out volume? Let's think about that. Because the gases within that styrofoam, that's not causing any mass there. So actually when they shrink the styrofoam cup, they're taking out volume. So let's think about this. If your mass stays the same and your volume decreases dramatically, what did you do to your density? Well, you've increased your density. So think about that mathematically, and we'll be doing some activities this week regarding that. So the next thing I want to show you is there are two types of procedures to find density. And this is some of the lab stuff that we're going to do, and I'm really excited about. First off, you can use a graduated cylinder and digital balance. And we have both of those in the lab that we use constantly, so you guys will be professionals very, very soon. And the second thing is you can use a burette, and that's what you'll see in this lower right-hand corner here. And we're actually going to be using these this week. And these burettes are beautiful because look how much skinnier that burette is in comparison to even a graduated cylinder. It's very, very skinny. So if you think about that, the skinnier the actual tube, the more accurate those little lines, the graduated lines on there are going to be. So we're going to take a look at this, and this is called this little turn thing right here. You just turn it and it allows the liquid to go through, and then we can read how much liquid we put in the bottom based on our readings here on our burette. So the last thing I want to leave you with here is how do ships float? So one thing is, I know I always have students ask with density, it's crazy to think about. If you've ever been on a cruise ship or if you've seen a cargo ship on the river or anything, you're like, good gracious, that sucker's huge. How on earth does it stay on water? Well, I want you guys to kind of see, first of all, look at this picture. You have the weight of the water displaced equals the weight of the ship. So we want to keep that in mind. And the average density of the boat, contents and air, is less than the gravity of water. So we're going to look at how much open space there is on these boats. So I have one little video to show you here.
Science!
So if I take this box and just obliterate it in the corner right here, and then put it in the water, the weight of the water rushing in will cause the box to sink. If I take this box and do the same thing, it tips over a little bit, but it still floats. This box uses the same kind of design that naval architects use to prevent ships 1,000 times bigger from sinking. What's so special about this box that prevents it from sinking, even with a big hole in its side? Let's talk about why ships sink in the first place. You probably know that things will float in water if they're less dense than water, and sink if they're more dense. The metal that this ship is made out of is way more dense than water, so you might think it would sink. But that metal is shaped so that it traps a lot of air, which is less dense than water, inside it. So the average density of the hull of the ship is actually much lower than that of water, so the ship floats. But if the hull springs a leak and fills up with water, there's no more air to lower the average density of the hull, so the ship sinks. The design of this box basically prevents too much water from getting into it. This box's hull was divided up into watertight compartments with these walls called bulkheads. So when I made a hole right here, only this compartment filled up with water. The rest stayed dry and were able to keep the box afloat. This box is subdivided, and so is this ship. Say the ship is divided into 10 watertight compartments. If one area of the ship got damaged, only that compartment would flood, but not any of the others. The added weight of the water here would cause the ship to tip over a little, to be angled or trimmed in the water, but it wouldn't completely sink and could still be taken to a port for repairs. So even with subdivision, why do ships still sink? Well, it's impractical and expensive to design an unsinkable ship, especially because most of the time, ships just don't see that much damage. What naval architects do now is try to predict what kind of damage is most likely to happen when designing a ship. Now, ships are more complicated than this box. Naval architects have to think about where to subdivide the ship, the shape of the hull, and equipment that goes into the compartments. We don't know when people first started subdividing ships, but accounts of Chinese trade ships as far back as the 5th century indicate that water would be able to enter the vessel without causing it to sink. It's pretty crazy that technology that existed so long ago is still being used today.
All right, so that is the last video, and hopefully you guys, either recalled some information or really felt like you learned a little bit more about density. Again, I'm going to Zoom with you guys if possible on Tuesday to answer any questions that you might have. But today, I do want you to work on the density calculations. And just like I told you, the substitute told you, I'd like for you to take notes over this video. So then we can discuss those when I come back on Wednesday. I'd also like to see those. Just for the year, you will want to take notes regularly. So you may, I'm not going to collect your notes, guys, so you can have, you can handwrite them, you can type them, but you need to have a place that you can go back and get to your notes, because you'll want to like keep your notes on the regular. So we'll talk more about that when I come back, but I'm going to leave you with this goofy little meme here. You can tell the gender of an ant by throwing it in water. If it sinks, it's a girl ant. If it floats, it's buoyant. Okay, so you guys will know my sense of humor is pretty crazy. I will see you guys soon, and I hope you have a wonderful day. Bye-bye.